Right. The end is nigh. We're getting close to the end of the quarter, which is a little scary, but probably also a bit of a relief. This week, we don't have a ton. We had an assignment due yesterday that I've extended for probably at least half the class at this point, which is absolutely okay, given everything that happened. As you get closer to submitting that, for those who don't have it in yet, let me know if an extra day would do you some good. And I just wanted to make sure that I didn't extend it for everyone. I think I mentioned this yesterday, but just so that the grader can get started grading those that are submitted to optimize turnaround time.
There'll be one more assignment after the 4 questions.
Yeah, we're doing a part 2 of the assignment that is due now, where we're implementing the graph algorithms that we've talked about. So you'll have implementations of Dijkstra's algorithm and Bellman-Ford and Floyd-Warshall, but in a strategy pattern that will make use of the structure that we have used so far. So there's one big assignment left. Yeah.
When is the exam?
Exam is a week from Friday. Last day of class. That I don't plan to meet during our finals period, during finals week, but there will be probably some assignment that, while it can be submitted before that, will be allowable to submit during finals week. I can't technically make an assignment due, but I can certainly extend something for everyone over that period of time without the expectation that you have that time. Those of you who do have the time, it's extra time.
What time regarding that?
See, beyond that, yeah, I'm getting you a study guide for the last exam by tomorrow. So you'll have that to look at over the weekend. My plan for today is we may finish up the approximation algorithms content. We may have a little bit left. I have carved out today and tomorrow for that. Next Monday and Tuesday, we'll be going over interviewing. And then Wednesday and Thursday, we'll be reviewing over that last exam on Friday. And that takes us right to the end of the quarter. Questions on schedule or due dates? I'm going to try to get the specification for that last big assignment to you today. I have drafted it and I am working with the grader to ensure that nothing needs to change after I get it to you. But I can discuss it in more detail, especially in office hours, if people would like to get started on that sooner rather than later.
I do have a question.
Yeah, sorry.
Those are the 4 problems we posted.
The slide deck that has them is up now. I'll get the official assignment posted today as well. So if you'd like to get started on them, look at that last published slide deck in the course, but it won't be anything different than here are some book problems. Submit the book problems. Sorry, yeah, you're just outside of my peripheral vision, so I appreciate your willingness to reach out and say, hey, I have something. It's not because I don't want to see you, it's because you're out of my peripheral vision, but I appreciate it. Anything else before we dive back in? Okay, we were in the process of looking at the vertex cover problem, which said that for every edge in the graph, at least one of the connected vertices to that edge is in the vertex cover. And we want to find the smallest possible vertex cover, the fewest number of vertices in the graph, such that for every edge, at least one of the connected vertices is in that vertex cover. Have we had any thoughts on this since yesterday?
You mean Tuesday? It's Thursday.
Yeah, we did something else yesterday.
We went over the exam yesterday.
Indeed, what we did.
You and I talked about this in OPSEC, and I just forgot.
Deep breath. The memories often come back when your mind is calm and able to flow freely.
So thoughts on vertex cover. We had a couple of good ideas floating around at the end of Tuesday's class. But we want to find an approximate solution, and we want to find a way to determine the efficiency of that approximate solution. We want it to be an efficient solution, but then we also want to ensure that we have a bound on how close to the optimal solution the approximate solution is in the worst case. But instead of focusing on running time, which is still important, we also have to focus on, since it's an approximation algorithm, how much worse than optimal could this be in the worst case? I'll have us working groups on the next one, but I'll at least give you one of these, I think. So here is an incorrectly animated slide.
My favorite.
Yeah, look at the solution. It doesn't have a solution. There it is.
Yeah.
So let's take a look at this code and see if we can figure out what it's doing.
Let's see, it says here, let's see, C is equal to what exactly? Is that theta?
That is the empty set.
Oh, okay, so. Empty set, okay, so then let's see, E prime is equal to G dot E, okay,
Edges of the graph G.
Yeah, that
So it
makes
takes the
sense.
parameter G, which is a graph.
that makes sense, we definitely need a color coded label type of thing for this, but I actually see it, let's see then. Yeah, then let U and V be an arbitrary edge of E, oh, and this is while E is not equal to the empty set. So let's see. C starts off as an empty set, then. We add. See, then we add that edge to C slowly by unioning it. And it removes that same edge from E and every edge incident on either part of that edge.
Incident here just means adjacent to, so if we're gonna look at every edge that is adjacent to the two vertices that are the endpoints of the edge that we select arbitrarily. We're going to remove every edge that's adjacent to the two vertices for the edge that we select from the list of possible edges, so that we can't select those for any reason in the future.
Four things.
Yeah, I'm gonna draw exactly that example. That seems like a reasonable one.
Yeah.
To draw. So if we have a graph that is just four vertices in a square with these edges, we could select an arbitrary edge. I'll use a different color for this. If we select this edge as part of arbitrarily, then we would add. We're going to add this to our list of covered. We're going to say we're going to add this and this to our vertex cover. Then we are going to remove this edge and this edge from the selectable edges. Then there's an edge that is left. So when we loop back around, the list of selectable edges is not empty. We're going to select this edge, which says that we take this and we take this. So our vertex cover in this case is every vertex. So terrible solution for seeing whether this approximate solution is efficient. But as graphs scale in size, we will see that this actually is relatively efficient.
What if it was 5?
Yeah, let's draw that out. What would we like a fifth edge, fifth vertex, and what do we want to connect it to?
The house.
Like a house. So we would have it wrong color. All right. We're going to select an arbitrary edge. What edge do we want to select?
What if we got rid of the one that was below the,
This one?
one more on that line?
This line? Okay. Let's select an edge at random. Anyone have a suggestion? Which edge should we take if this is maybe 1, 2, 3, 4, and 5?
5.
5. We'll select this edge at random. We select this edge, which says that this is in our vertex cover and this is in our vertex cover. Then we're going to remove this edge and this edge. So the only edges that are left are edge 1 or edge 2. Which one should we select?
Does it really matter?
Thinking two.
2. So this is an edge that is selected. So that tells us that this vertex and this vertex are in our approximate vertex cover. And then we would remove this edge because it is adjacent to this selected vertex. And now we can terminate. There are no more edges that are either selected or removed as part of the removal process on line 6 here.
So we would say edge 2 and edge 5, but then with the note out.
Yeah. So it still doesn't look great, but we would find that as the graphs get bigger and more complicated, this approaches and is limited by twice the size of the optimal vertex cover. And as these graphs and edges get very large, the optimal vertex cover is going to be smaller and smaller with proportion to the graph as a whole. So doubling that is going to give you an approximate vertex cover that's going to look better than it does in either of the last couple examples that we've used here. But let's actually look at why that is, because I think that is important to try to figure out the logic of why we get twice the size of the optimal vertex cover. First of all, any questions on the algorithm? Yeah.
Yeah, I just wanted to say, based off of how the algorithm is shown, I assume the density of the graph doesn't matter as much.
Yeah. So I guess we could start by looking at the worst case running time here. We're looking at most all of the edges as we do this, and as we do that, we're going to be looking at the vertices that are adjacent to it. So the most work we can possibly do for this is related to the number of edges plus the number of vertices in the graph, which is polynomial. That is not exponential like the actual vertex cover problem is of finding the optimal vertex cover. So this will give you an answer in polynomial time. The question is just, how good is that answer? We're going to say that the set A is the set of edges that this process picks. So in the last example, we picked 2 of the 5 edges. So those edges are this set A. We know that an optimal vertex cover has to include at least one endpoint of each edge, right? That is the definition. First of all, is that possible with this process? If we were to select edges in the absolute perfect order, would it be reasonably possible to produce an optimal vertex cover? The answer is yes in special cases. It is possible, but it is not probable. We know that, in this case, no 2 edges in that share an endpoint vertex. Does that make sense? That would be saying that if we have 2 edges, we have this edge to a vertex and this edge. If we selected this edge as part of our selected edges in the last algorithm, we would have removed this edge after doing that. And if we had done the exact opposite, if we selected this edge, then we would have removed this edge as part of that, since we would look at the connected vertices and remove the incident edges connected to that. So there's no way that 2 selected edges share a vertex. Means
Could we discard
self-directed edges.
Yeah, we would not be needing to consider those as part of a vertex cover. We're gonna define an edge that, since it is UV and not possibly UU or VV, we'll just make that extra constraint that U and V cannot be the same vertex. And that would do it. That would get rid of all self edges. Good question. So this helps us to get a lower bound that the vertex cover is the optimal vertex cover. Just with that one assumption, we can show that. So that gives us a lower bound. It is possible for approximate vertex cover to give us the optimal vertex cover. But what's the upper bound? What is the worst case for what this could be? We told you what it was, but why? When we pick a new edge, neither of those endpoints can be in the existing cover. If they could be, then it would have been an incident edge for one of the past selections of the edges. Does that make sense?
Does to me.
So we pick a new edge that has two vertices adjacent to it. If this edge had been selected, then this edge wouldn't be a selectable edge. If some edge adjacent to this had been selected, then this wouldn't be a selectable edge. So we know that this is not already in our vertex cover, and this is not already in our vertex cover, by definition. That's all that is saying. So because of that, that gives us that upper bound, 2 times the size of the lower bound. If the lower bound says that no two edges share an endpoint vertex, and then we can also show that neither of the endpoints of a newly selected edge are in the existing cover, that tells us that we're selecting at most 2 times the optimal vertex cover in this process. Since ideally, we would want to be able to select one of the 2 endpoint vertices rather than both of them. The fact that we're selecting both of them to be in the optimal vertex cover here gives us that upper bound. If we could only select one of the 2 vertices, there'd be no guarantee that the end result of this would be a vertex cover. But we get the guarantee that with this algorithm, we do get a vertex cover. And because we're using a process that selects 2 vertices connected rather than 1, that is the reason why we get twice the optimal cover as the upper bound. Any questions on that idea? Clarifications on that idea? So we just need to use logic to give those bounds. And in small graphs, twice the optimal vertex cover is going to look really bad. When there are 5 vertices and the optimal vertex cover is 2, then twice the optimal vertex cover is 4 of the 5 vertices. So given a sparse graph like that, it's going to look bad. But a dense graph would look better. And a larger graph would look better. So this scales to be more efficient and a better representation of the optimal vertex cover as the graph scales in size. I'll give you an example. Here is a graph. Let's say we select this edge. If we select the edge BC, then we take all incident edges, AB, CE, and CD, and we remove those from the selectable edges. Then we loop back around, we'll select another one of the non-dotted lines, filled lines. Let's say we select the edge EF. Then we take and remove the incident edges from there. And that leaves us with a single edge left to select. So we do that. And every blue vertex is part of our approximate vertex cover. And so we end up with this as the result of the approximate vertex cover. And we see that this is the worst case selection because the optimal vertex cover is half that size. We made the absolute worst decisions that we could for this. What would the best edge selection have been if we, starting at the very beginning, wanted to produce the optimal vertex cover? Is it possible to do in this graph?
Is that D and
Yeah,
select that edge?
yeah, so if we look at the optimal vertex cover, we would want to select the edge, since we're going to be adding both vertices from that to the approximate vertex cover, we would want to do that. But with this graph, there is no way to get the optimal vertex cover because we need to select, we would be removing all incident edges, so that would remove EF, DF, and DG, as well as CD and CE. So we would need to pick one of these two edges. But there's no way to know for sure that, like, according to the past process, we'd be adding either B and C or B and A to our approximate vertex cover. So we could have gotten an approximate cover of 4 vertices rather than 3. The thing to note is, since they share a vertex, everything that's left shares a vertex, we could try to optimize that from there and select the shared vertex. And that would have allowed us to select a 3 vertex approximate solution. But even that process doesn't necessarily scale effectively and in general. How are we doing? Any last minute questions on vertex cover or approximate vertex cover?
I'm not sure if it happened, if I'm being honest.
All right, we'll look at another very common NP-complete problem, and that is the traveling salesman problem. I think I might have talked about it in here at one point very briefly, but who's heard of the traveling salesman problem before? Most people.
It feels familiar, yeah.
So the traveling salesman problem says we have a graph and we want to find the minimal edge weight Hamiltonian cycle. And I haven't described what a Hamiltonian cycle is, but that is a cycle that visits every vertex, starting and ending at the same vertex. The idea of the traveling salesman is that gas prices are ridiculously expensive right now. So we need to figure out, if we are a traveling salesman, that our home is in Spokane and we want to visit some set of other cities to sell our wares. We want to minimize the total travel distance starting at Spokane, ending at Spokane, and visiting every city that we want to sell our wares. But there are lots of roads in between all of those cities that we want to sell our wares in. So how should we plan our route so that we start in Spokane, end in Spokane, and have the least gas costs because we've traveled the least distance between all of those cities? So that is the traveling salesman problem. So starts at a home city, must visit every city to sell their wares, ends up back home at the end. We can't strand the traveling salesman somewhere other than their home city. So goal is to minimize the gas cost and the environmental impact. This problem again is NP complete. Any intuition as you hear or think about this problem as to why it might be NP complete? Why is the worst case for this, or the best case for this, exponential if we're looking at all of the possibilities? Why can't we make intelligent decisions that would remove this from the exponential complexity and bring it back into polynomial?
That's a great question. First, good land. Nice.
Yeah. The issue is we're not trying to get from Spokane to each city. We're trying to get from. Yeah. So how many total paths could there be? Let's start by assuming there are, I don't know, 5 cities. What are the options for the first city we visit after Spokane? Spokane is one of those 5 cities. Yeah, there'd be 4 options. We could either go from Spokane to city number 1, Spokane to city number 2, Spokane to city number 3, Spokane to city number 4. Does anything about the shortest distance between city 1 and city 2 tell us anything about the best path there? Could be, but is it guaranteed that the closest city to Spokane is the first city we should visit?
City from that could be like 100 miles away.
Yeah, yeah. So we have to look at the entire path. We can't approximate and make a decision about where to go next, one step ahead or two steps ahead, because the horizon effect kicks in, where we may optimize one step ahead, but then two steps ahead, that decision looks ridiculous. One way to think about this might be, I like to use the game of chess to say that if you look 6 moves ahead and you come up with the optimal position 6 moves ahead, on the 7th move, they capture your queen, making the whole optimization of 6 turns look stupid in hindsight. It's very similar with the traveling salesman problem. You can optimize 1 city of travel or 2 cities of travel, and that may not be part of the optimal solution to 3 cities of travel. So let's again break into groups and see if you can come up with an approximation algorithm for the traveling salesman problem. We no longer care about finding the best path. We just want to find some path that is within some factor or scalar of the best path. And it is okay that that is the case as long as we have a polynomial time approximation algorithm. We can no longer be saying for each possible path of length 2, what is every possible path of length 3? And then optimize from there. That's going to be exponential in the worst case, but let's actually get in groups of 3 or 4 people and talk this out. What would you do to solve this problem relatively efficiently?
Good join you guys. Sorry. Alright, well, I'm just gonna first. Alright, I think,
Is no idea.
I really.
No, we do. Chris is just an empty sleep.
Surprisingly, not really.
So there is an optimal for it.
There is an optimal solution. It is relatively exponentially complex, but there are optimizations to it that allow us to make good decisions.
Yeah. Just as a,
It's the horizon, how many moves into the future that makes it difficult. So it is NP complete to solve perfectly, which is why no solution exists. But there are very good approximation algorithms for it that we can actually show what the best moves are, which is why chess engines can always show you what the best move is in that particular position.
Yeah.
Based on significant amounts of training.
not only that, but yeah, just this game where the first time you use the one second to last mistake.
Chess is a very interesting game when you dive into.
I actually have a lot of fun celebrating things. Believe it or not, I was in a chess club when I was in middle school.
I think it's why that's this is complicated. Chess is
We haven't added chess to that, but it is a challenging problem. It is a very challenging problem. But it's because it's not something that we can optimize. There's a give and take to it. The opponent gets to move and either make the optimal move or a non-optimal. So we have to solve it for every possible move the opponent can make at every position.
Whereas this is just one problem.
Yeah,
And chess is like an evolving.
yeah.
Problem.
Well, if you are interested, take my AI fundamentals course, because we talk about searching. Every AI problem is just a searching problem in a vast multi-dimensional space. Trying to find an optimal path or an optimal function or an optimal thing. There's something that we are searching for. And chess can teach us a lot about search. Because it's a reasonably large but understandable search space. And the search depth is reasonably deep. And it's adversarial in that you can't just, you're not fully yourself, the agent in charge of what happens, what unfolds. You have to make every contingency based on every move your opponent could. Yeah, no. Then you realize the go what he's talking about.
Yeah.
Go is such a fun
Yeah, the best-
game.
Best approximation algorithm, so. Well, yeah, so.
You make solve this.
To be honest, this is like going like, big circle round, so I'm just going to, draw out the example, so like. Got a bunch of cities and then. Gonna make some unique, edge connections and, so yeah, they want. But they have to visit every city and they have to do the most optimal path possible.
There's one path.
Well, no, I mean, in theory,
Start here.
yeah, it's pretty much. So it says here, that each vertex that starts ends with the same vertex, so let's say we're starting here. Then. And doesn't need to hit all these cities. One way to do it, it all depends on the don't know that. So then we could do like it in a big circle, or we could try doing it like say.
Because I think we have two problems with extras. At least.
Yeah.
But we also want
Oh, dude. I'm guessing the problem I do create in the last assignment will be sometime.
But we need to figure out some way to figure out the best, it's. Well. And we start again. Yeah,
Keep doing that, we run into a dead end.
I think you have the right idea, I'm not sure, but I think you have the right idea. This is an NP, this is meant to be an NP problem, so. You have to build in an algorithm that does. I have not.
One thing to remember about NP-complete problems is that we can verify a solution in polynomial time. So if I told
Yeah.
you what the best path is, you could tell me yes or no, that is the best path in polynomial time. If you've come up with a solution or have an idea, try to quantify it. How much worse than an optimal solution is your solution? Quantify that trade-off.
Let's. Well, let's see, the best trade-off would probably be like, since it with that, like, you're trying to brute force your way through every pathway or just trying to do like show it, that, it's a bit from here. Take about exponential time trying to figure out your path, so, define the optimal.
There be negative weights in this.
You can see it's.
Let's assume there are no negative edge weights.
At least this time, yeah.
How would you there
Yeah,
check other. You get the edge rate.
great question.
We want to answer.
I wish it was a better. You don't wanna have successful ideas that I do.
Yeah. I'd love to hear what ideas have people come up with so far. I think I've heard a couple of them.
I currently have an idea of just, doing some of the programmer stuff, reusing the vertex cover thing, just adding, adding thing to check, like, pick the lowest edge weight. And then do that until it reaches all the cities.
Yeah, knowing that something is NP complete means that there's also a reduction to another NP complete problem. So it is very useful to think about how is this related to another NP complete problem, either that we've studied or that exists. This was added to be NP complete by converting some other NP complete problem.
It makes sense.
I like that thought process. Anyone else want to share their thoughts so far? All right, I will give you a hint.
Minimum spanning tree.
Incorporate somehow the idea of a minimum spanning tree. What was a minimum spanning tree?
No. No. Now depth first search, well, that's actually not the worst idea, but.
A minimum spanning tree was the shortest possible cumulative edges that connects every vertex to every other vertex. So there exists some path from every vertex to every other vertex. And the minimum spanning tree was one that had the minimum edge weight, and it was calculable in polynomial time. Prim's
Yeah.
algorithm was very efficient. In fact, it was greedy.
Yeah, so basically, what you're basically saying in this case is we'd be building an algorithm that would. Pretty much act like a minimum spanning tree, only this time with our little traveling salesman probably.
Yeah.
Just quickly mapping out the. Like going down the tree, trying quickly mapping out the shortest, sorry, the lowest edge weight for. That
Yeah.
get us through every vertex and return back to the start.
So if we started with a minimum spanning tree, it would be possible to kind of depth first search that minimum spanning tree and be able to get from the starting vertex to every other vertex, but that would be highly inefficient. Not a good approximate solution. But could we expand on that idea? When could we decide that based on some search, some traversal of that minimum spanning tree, when could we decide to take one edge and use another edge instead? What do I want to? I want to go to the next slide. Probably not. Well, let's say we have a minimum spanning tree and a graph that you can draw something relatively small here. Let's say we can get here, 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 and here, and this is our minimum spanning tree. If this is our source, this is where we need to go and get back to. There are other edges in this graph that are not part of the minimum spanning tree. But we would then do something like traverse this minimum spanning tree in a way that visits here, then here, then here, then here, then here, then back, then back, then back. What do we notice about the path that we've seen so far? It's a lot of backtracking, but it's also twice the length of the minimum spanning tree.
Sense?
Why would we want to do something like, instead of going here, then back, that's this edge once and this edge twice? When would we want to decide to use this dotted edge, where we could now do this and that, instead of this, that, and that? If that makes sense. We could utilize edges that aren't in the minimum spanning tree, but we could use this traversal of the minimum spanning tree as a way to determine when to use edges that are not in the minimum spanning tree? Is there an assumption or something mathematical that we could use to decide to do that? And then what would that say? Can we quantify how much worse than the optimal path something like that could be?
I think we could.
Yeah, so just start by thinking of this idea of let's depth first search the minimum spanning tree, which takes twice the cost of the minimum spanning tree. That's not the optimal solution or close to the optimal solution. But it gives us a baseline for which we could use a polynomial time algorithm to improve on.
I really should be.
So think about this in your groups again and see if you can come up with something about this.
What other paths you left? After we discarded the.
I have to give that hint because I don't think anyone in here would have come up with it. It's actually
Over there.
Not the worst idea in the world at least, but I don't know if that's the right answer.
as is definitely not the right answer, but it's the baseline of an optimization to this.
Yeah.
That is the best we know for solving this problem.
I'm sorry, I'm just not really finding anything here. I don't think anybody's.
Yeah,
I have an idea,
Yeah, what are you thinking?
Need your thoughts on it. So, obviously, you performed the minimum, spanning tree.
Mm-hmm.
And once you, let's say, traverse it once and reach the final node. Would it be beneficial to then perform a dexterous from there to return back to the start?
Interesting. Very interesting. The issue is there may be multiple destinations where we want to try to do that. So like if we were at this node here, we would want to visit the nodes we haven't seen before returning back. And I would feel like we've already made a mistake by taking potentially this sequence of paths.
Okay, that's fair.
But no, that's a great start or a great idea. What we're going to end up needing to use is the concept of the triangle inequality. Has anyone heard of this before?
I assume it's not an equilateral triangle.
No,
For any triangle, there's something we can say about summing the length of two of its edges with respect to the length of its third edge.
yeah. I think it's.
So we have some triangle. Doesn't matter what the shape of this triangle is. Does not matter. I don't want to draw something too something that's too symmetrical. But if we have length A, length B, and length C, what is guaranteed about the length of C compared to length A plus length B?
It's going to be longer.
Yeah, A plus B has to be longer than C. A plus C has to be longer than B. C plus B has to be longer than A. Otherwise, it's a line. It's equal to when it's a line. If we took this third point and we moved it onto this line, then B plus C would be equal to A. But in order to separate it and make a triangle, that has to always hold. So how can we use that idea when we're looking at something like the minimum spanning tree is telling us to move along this edge and this edge? And then we have to go back to this edge. When would we want to use this edge or this edge instead of going back? And we could connect parts of this in different ways.
Okay. Well, when we want to use it, it would probably be when. Let's see, one. Yeah, depending on the edge weight, it would be the shortest edge weight if we did go up that edge with respect to the other two. Check me if I'm wrong.
That's right.
Right, see, so there's a reason you drew it as.
I always try to foreshadow.
I really am gonna have some serious conversations with the staff about getting better at these problems.
I hold class the way that I do so that people recognize it's not necessary, there's no blame for not being where you will need to be eventually, but also this is the practice. It's recognizing the problem solving process and utilizing everything you've ever seen and some things you haven't seen in order to solve problems. Yeah.
I suppose then the idea would be after making the minimum spanning tree, you would see if any node attempts to revisit another node. Then you would check if the total of the two traverse paths is less than the untraversed path.
Yeah,
I like it.
I like that idea a lot. So we are unfortunately basically out of time, but I wanted to at least get through this much of this problem so that, yes, a lot of you are going to be working on the assignment between today and tomorrow, but if I have piqued your interest, try to formalize this a little bit or work through some of that logic where you could use the concept of the triangle inequality on a depth first search of a minimum spanning tree in order to get an approximate solution to the traveling salesman problem.
Now I'm seeing somehow make it a That's
So yeah, I have office hours starting now. And I'm happy to help anyone in whatever way I can. Yeah,
Oh, in that case, a little slower.
yeah.
I had it. Yeah. Oh, but, like, yeah, you pick out my.
Sounds good. I'll meet you at my office.
Ah,
That will probably be the best way to do it.
I see. Well, in that case, see you now, or that class.
Oh, if it's something really quick, then I can answer it before your class.
I guess my real quick thing is the